Good morning students, I hope you all are good. In our previous class, we have discussed lesson 4, electromagnetic induction and alternating current. Especially what we discussed means electromagnetic induction, Faraday law of electromagnetic induction, magnetic flux, Faraday's laws, Lenz's law and conservation of energy from Lenz's law, motional EMF from Lorentz force. Today we are going to discuss motional EMF from Faraday's laws. What is our today topic? Motional EMF from Lorentz What is our topic? Motional EMF from Lorentz force. See the board? So we will derive the motional EMF where means Lorentz force. This question already we are discussed in our previous class. So just I recall that equation. So EMF represented by the symbol psi equal to BLV. This is the motional EMF. When the motional EMF, they produce induced current. I is equal to psi by R. Isn't it? So today we are going to discuss another important 5-mark question, motional EMF from Faraday's laws. So what is that? Motional EMF from Faraday's laws. What is our topic? Motional EMF from Faraday's law. So I will consider uniform magnetic field. See that the uniform magnetic field represented by cross symbol. This is the uniform magnetic field. This uniform magnetic field represented by B vector. Here B vector means uniform magnetic field. This uniform magnetic field, how that acting means it acted perpendicular to the plane of the paper. Here we can't able to see if using the paper. Suppose I will draw one diagram. See that? Assume this is the paper. When the uniform magnetic field enter into the paper and comes out to the paper, see that direction I will show that. This is paper. The magnetic field is perpendicular to the paper or paper is perpendicular to the magnetic field. In the same diagram I have drawn here, the magnetic field perpendicularly acting to the paper inward that represented by the symbol cross. Got it? So what is the cross symbol indicating? The magnetic field is perpendicularly acting towards the paper or in plane of the paper. How that means into the paper, inwards. How that acting? Inwards. Next time, I will take a rectangular loop. What is that? I will take one rectangular loop. The rectangular loop is ABCD. See, I will take the rectangular loop. The rectangular loop sides are AB and CD. See the diagram. The rectangular loop ABCD. One part is inside the magnetic field, other part is outside the magnetic field. The rectangular loop ABCD. One of the part is inside the magnetic field. Remaining part of the loop, these are the remaining part of the loop. This remaining part of the loop is outside. Remaining part of the loop outside. You will see the board. So one part of the loop inside the magnetic field, other part of the loop is outside the magnetic field. That means the other part of the loop is not in the magnetic field. Here the length and breadth of the magnetic field is L. The length breadth of the magnetic field we are considered to the loop is L. What is here L indicating? The length and breadth we are denoted by L. Next, we have to pull the loop in the side AB. So, pull the loop in the side AB with constant velocity V. What is that? Constant velocity V. What we will do when the loop is pulled or pull the certain constant velocity in the right side of the magnetic field. See that? Right side of the magnetic field. What happens means the loop is changed the position. That means rectangular loop is changed. How to change it means when you pull no. See that? The position of the loop. This is the when due to the pull, the loop is moved certain distance. The dotted lines is a moved position, and the original position represented by continuous line. So this is CD, C dash, D dash, the new position A dash, B dash, and original position A, B. Due to the pull of the the rectangular loop moved certain distance, the magnetic field on the loop going to decreases. See that? What is that? The magnetic field on the loop going to decreases. So magnetic field on the loop magnetic field on the loop decreases. So now magnetic field decreases means the magnetic flux. What is that? Flux also decreases. The magnetic flux also decreases. According to Faraday's laws of electromagnetic induction, according to Faraday law of short form of electromagnetic induction, changing the magnetic flux linked with the closed loop, they produced what they produced? Induced current. This induced current opposes the decreasing the magnetic field. Which law means? It is based on the Lenz's law. According to Lenz's law, the induced current opposes decreasing the magnetic flux or opposes the pull of the loop. what happened? The induced current, actually the induced current always oppose the cause. Here cause is the change in magnetic flux. Here change magnetic flux is decreasing magnetic flux. The decreasing magnetic flux is to be cause. That cause is to be the induced current going to oppose. Here how to oppose means the induced current produce the magnetic field in the same direction of the already present magnetic field. For example, this is the magnetic field, uniform magnetic field in the paper, plane of the paper. When the induced current is produced, no, that induced current produce the magnetic field. That magnetic field also in the same direction of the already present magnetic field. So it opposes the decreasing magnetic field or magnetic flux, or otherwise we call oppose the pull of the loop. The pull of the loop oppose means the decreasing magnetic flux also. What happened? It stopped. So once again, motional EMF from Faraday's laws. I will consider uniform magnetic field in the plane of the paper. How that uniform magnetic field means is perpendicularly inward, acting inward in the paper. And I will take a rectangular loop ABCD. In the rectangular loop, one part of the loop inside the magnetic field and the remaining part of the loop is outside of the magnetic field. Here outside of the magnetic field, the loop is not present in the magnetic field. Next, I want to pull the loop with constant certain velocity v. Due to the moving due to moving constant velocity of the loop, the magnetic field on the loop going to decreases. I showed that how the magnetic field going to decreases. The magnetic flux also decreases. According to Faraday's law of electromagnetic induction, the induced current is produced. The induced current is responsible for oppose the decreasing the magnetic field. That is based on the Lenz law. We already discussed in our previous class Lenz law and the illustration. Otherwise, oppose the pull of the loop. So here, next. Once again, I will draw the diagram. This is length. The magnetic field present in the loop is considered to be x. So area of the loop we will calculate it. Area of the loop is nothing but x into L. That means length into breadth. No, here length is x, breadth is L. So Lx. What is that area? Next, when the movement of the loop with the constant velocity, they produce magnetic flux. No, the magnetic flux represented by symbol pi b equal to. We already discussed the mathematical equation. In that line integral area b vector dot dA vector. What is that? B vector dot dA vector. So here B A cos theta, or here theta is considered to be 0 degree. So B A cos 0 degree. We know that cos 0 degree equal to 1, isn't it? So what is the magnetic flux? Pi b equal to BA. This is equation number 1 and this is equation number 2. Substitute equation 1 in equation 2, what we will get? The magnetic flux pi b equal to magnetic field, that is constant uniform magnetic field. So what is the area we are already discussed? Lx. Pi b equal to Blx. This is equation number 3. When the movement of the loop with the constant velocity, they change the magnetic flux due to how much magnetic flux is produced. We have to find first we have to calculate the area of the loop. So area of the rectangular loop is considered to be length into breadth. Here length is x, breadth is L. So area equal to L into x. Next, we already derived the mathematical expression of magnetic flux. Pi b equal to line integration of b vector dot dA vector or BA cos theta. Here theta equal to 0 degree. Cos 0 is 1. So BA cos 0. So cos 0 is nothing but 1 into BA. We are getting BA. So substitute equation 1 in the equation 2. What we will get? We are getting the new equation. Equation number 3. Pi b equal to BLX. Okay. So next. As the magnetic flux decreases, an induced EMF is produced according to decreases according to Faraday's laws. Induced, what is that? Induced EMF is produced or obtained. So induced EMF represented by symbol psi equal to d pi b by dt. What is that? D pi by dt. Equation number 4. So how that equation obtained means, as the magnetic flux decreases in the loop due to decrease in the loop, according to Faraday's laws, the induced EMF is produced. That induced EMF represented by the equation, already we derived the equation, psi is equal to d pi by b by dt. So now we have substitute equation number 3. 3 where means in equation number 4. So left side of the equation we don't want to change. What is the left side of the equation number 4? Psi, that means EMF, then d by dt. So equation number 3, see that pi b equal to BLX. So substitute instead of pi b, what do I want to substitute? BLX. Here that magnetic field and length are constant. So I will write first. What is the next term? D into x dx by dt. Next step, I is equal to VLB. How that V came means in the lower classes, 10th standard, also 11th standard, we discussed what is the velocity means. Velocity is nothing but V equal to dx by dt. Displacement with respect to time. So what is the final equation? The induced EMF equal to, instead of dx by dt, you can write that what we want to write? BLV. This is our required equation. The required equation is equation number 5. The required equation is, what is that? 5. The required equation psi, that is induced EMF equal to BLV. Here V means how that V obtained dx instead of dx by dt. V is equal to dx by dt. That means velocity. This EMF is known as motional EMF. This motional EMF is obtained by, how that obtained means due to the movement or pull of the loop. How that motional EMF is obtained? The motional EMF is obtained due to the movement or motional. The EMF is obtained due to you have to move on with the constant velocity, the loop. That reason the EMF is produced. Okay, got it. Next, suppose when the loop is connected to, where we want to connect it means, see the diagram, connected by an external circuit. The external circuit consists of resistance. So how much current in the circuit produced, we can identify using the equation. Already we derived the equation. I is equal to psi by R. This is equation number 6. Already we are got the value of psi in the equation number 5. So substitute the equation number 5 in equation number 6. Substitute the equation number 5 in equation number 6. What we will get means the new equation. What is the new equation? Induced current. Induced current. I is equal to, what is psi? Substitute that. Instead of psi, you have to write B L V by, what is that? R. This is the required induced current equation, and equation we call equation number 7. So equation number 5 is the motional EMF. Equation number 7 is the induced current. Due to motional EMF, they produced induced current in the given electrical circuit. Okay, so motional EMF from Faraday's laws. The equation number 5 and equation number 7, they are always asking 1 mark questions, some NEET and JEE examination questions and preparatory exam questions also. So what you will do is you will be thorough in the question in the equation level and also theoretical level and also diagram level. Okay. Next, we will going to see that we are going to discuss conservation of energy. What is that? Conservation of energy. Motional EMF, already we have derived a motional EMF from Faraday's laws. And conservation of energy. Already we derived what we derived motional EMF and induced current. What is the motional EMF? Psi, just I read the equation that is required, BLV by R. What is that induced current? I is equal to, motional EMF is BLV, then induced current is BLV by R. Just I return the box with 2 equations. This equation is must to prove the conservation of energy. The motional EMF from what laws? Faraday's law. So already I drawn the diagram. Now I rough once again. I will draw. See. I will consider uniform magnetic field. In the rectangular loop, ABCD. In order to move the loop certain constant velocity v, the loop is moved certain constant velocity v. What happens means they produce the force. The force is equal and opposite to the magnetic force. Must be applied on the loop. So in order to move the loop with certain constant velocity move in the right side, the force must be applied. That applied force must be equal to magnetic force on the loop. In order to move the loop with constant velocity v, in order to move the loop with constant velocity v towards right side of the magnetic field. So that is uniform magnetic field represented by the symbol B vector. So a constant force is equal. A constant force is equal and opposite for what? The magnetic force. Magnetic field produces magnetic force. Must be supplied to the loop. So some work has to be done to move the loop with the magnetic field. So therefore the mechanical work must be supplied. The mechanical work must be supplied or done, must be done in the loop. So that is we call as rate of doing work. What is that? Rate of doing work. The rate of doing work in the lower classes we have discussed is nothing but power, isn't it? What is that? Power. So power represents the symbol P equal to F vector dot B vector. Then we want to write the equation in the other form. F V cos theta. If theta is equal to 0 degree, already we will cos 0 equal to 1. Substitute P is equal to F V because cos 0 value 1. When you substitute that, instead of theta 0 degree we are getting 1. So 1 into F dot V we are getting F dot V. This is equation number 1. What is that? Equation number 1. Now let us find the magnetic force. Now let us find the magnetic force acting on the loop because the loop present in magnetic field. So we have to see, or we will see that 3 deflecting magnetic force present in the given loop. What are the 3 magnetic deflecting magnetic force? Means F1, F2 and F3, etc. I will show that how that the magnetic deflecting magnetic force acting on the loop. See here, this is the constant force. We are supplied already due to the moment of velocity. Next, the force here at F2, magnetic deflecting magnetic force. Another magnetic deflecting force is F3, and this force is F1. So 3 deflecting magnetic force present in the given loop. What are that? F1, F2, F3. and F is the constant force we are supplied. Due to the magnetic deflecting force, the general deflecting force equation. So here we can write Ft. What is here indicating? D means deflecting force equal to I small I L vector into B vector. This equation we have derived in our previous chapter, third lesson, magnetic effect of electric current. IL into B vector. IL vector into B vector. See the board, see the diagram in the board. The forces, what are the forces? F2 and F3 are acting opposite direction, so cancel to each other. Equal magnitude. Suppose for example F2 is 5 Newton, F3 also 5 Newton. Equal forces opposite acting in the opposite direction, so cancel to each other. Got it? What are the remaining force? Only F1 force. The force F1 is alone. Where is means in the left side of the loop. Now to find the deflecting force on the F1. So what is the deflecting force F1? Already general equation of deflecting force we are derived the equation number 2. The same equation we can use that F1 equal to the force F1 only present. F2, F3 are cancelled to each other. So F1 equal to IL vector into B vector. Other form, F1 vector equal to IL B sin theta. Here theta equal to 90 degree. What is that? Theta equal to 90 degree. Here what is theta? Theta is nothing but the angle between, for what to what means, the angle between direction of the magnetic field and length of the loop. The length of the loop is represented by L. So what is here theta? Theta is the angle between direction magnetic field and the length of the loop. So what is theta? 90 degree. Now substitute instead of theta 90 degree. We are getting the magnetic force deflecting equation IL B sin 90 degree. So sin 91. So F1 equal to IL B. This is equation number 3. So how that equation is obtained? You remember that because what is that? Sin 90 degree equal to 1. The trigonometric table, sin 90 equal to 1. So the applied force, therefore the applied force, what is here applied force? F vector is the applied force, that is equal to, must be equal to the force F1 vector. F1 vector. When means the loop move with constant velocity. The condition is loop move with a constant velocity. So we can write F vector equal to minus F1 vector. Here minus negative sign indicates the force in the constant force is opposite direction of the deflecting magnetic force. So substitute equation 3 in equation number 4. We will consider only magnitude, not in the direction. Consider only magnitude. So what is the reason I consider only magnitude? Means they are not showing the direction, means we don't want to consider the negative side. So F vector is nothing but what is F1? ILB. This is equation number 4. Got it? So how that equation number 4 obtained? Because the applied force must be equal to the deflecting force. When means the condition is the loop moves with a constant velocity. So next use the equation number 4 when we are rate of doing work. Already we have discussed, no, rate of doing work is what is that? It's nothing but power. To find the dissipation of power, so already we have derived the equation power. So P equal to F dot V, isn't it? Now we have to substitute the equation number 4 in the equation number 5. So equation number 5. Next, now we have to find the equation number 4. See the equation number 4. What is the equation number 4? That indicate right side of the equation ILB. Already we derived. See the board. What the induced current? The induced current value substitute in the equation number 4. So we are getting force equal to what is that? ILB, isn't it? Now we have to substitute I value in this equation. We are getting the applied force equal to, instead of I will write BLB by R. What are the remaining terms? L into B. Now I multiply B into B, B square, L into L, L square, B by what is that? R. So F vector equal to, this is the constant force. This is equation number 6. So the equation number 6 is the constant force we are applied to the loop due to with the constant velocity. When we apply the mechanical work, no, that mechanical work is converted into power. The rate of change of work is nothing but power. See the equation number 5, power equation, P equal to F dot V. Equation number 7. Substitute equation 6 in equation 7. What we will get? So power equal to, instead of F, what I want to substitute? B square L square V by R into V. So what is the final equation? If I multiply V inside the equation, so power P equal to B square L square V into V, V square by R. So this is the power. So the power of the applied means the rate of change of your applied mechanical work where in the loop, that is converted into power. That is converted into power. When the current flows through the, what current means? Induced current due to producing of induced EMF, produce induced current in the circuit. That is the final case. When the induced current flows through the loop, What happened means that current is in the form, another form. What is that means? Joule law of heating. What is that? Joule's law of heating. So according to Joule's law, in the lower 10th standard itself we are derived the equation. What is the equation? H is equal to I square R T. Here T we are calculated 1 second. And R resistance. Next, instead of H, I want to write that power P, because heat is also we are dissipated. No, at what form? Joule law of heating. So power for H I will write P I square R. T equal to 1 because time equal consider 1 second. Already we are derived the equation, current equation. Where is that current equation? I equal to BLV by R. No, now we will substitute. So P equal to, see that instead of I, what I want to write from that equation? BLV by R. So BLV by R to the whole square into R. Square on the equation in the bracket, B square, L square, V square by R square in the numerator R. So R in the denominator will cancel. So what is the final equation? P equal to V square, L square, V square by R. So our last equation is 7 and we are getting power equation is 8. We are due to the induced current flows through the loop. The induced current is converted into another form. What is that another form? Means Joule's law of heating. It is converted into heat. That means the mechanical work is converted into heating effect or heat energy. So the mechanical work done moving the loop is appeared to thermal energy. What energy? Thermal energy. That thermal energy represented by we are done some mechanical work in the loop. No, we are moving with constant velocity. That is the mechanical work. That mechanical work is converted into in another form. What is that form? Means thermal energy. Thermal means heat energy. It is based on, this is repeated one more question. The motional EMF from Faraday's law and conservation of energy is converted into what type of energy? It is nothing but form of thermal energy. This is a repeated 5-mark question. Always this question will ask. Actually, in the previous year this question is not there, but this year they are gave that this question. So motional EMF from Faraday law and conservation of energy. Conservation means the energy is not created, not to be destroyed. It is nothing but is converted one form into another form. Here one form we are, what form we are applied? We are applied mechanical energy. That mechanical energy is formed thermal. Thermal means thermal energy. I hope this question is a little bit difficult. So what you will do means if you write number of times and check self-evaluation and you will write in the examination. Always remember the certain equations. What are the equations? Induced EMF and induced current. Use these two equations, we can prove that conservation of energy. Is same for that motional EMF from Lorentz force. Okay. If you have any doubt, please ask. Thank you.